Hello and welcome to our webinar today on nutrient monitoring. I'm Nick Rendell with Hach Hydromet, and today we will be hearing from two of our Hach environmental sister companies, Satlantic and WET Labs, two leaders in the field of nutrient monitoring in both coastal and freshwater applications. Our first speaker today is Dave Gillette with Satlantic, and he will be presenting on the SUNA ultraviolet nitrate sensor.
Hello, as Nick mentioned, my name is David Gillette. I'm with Satlantic. I'm a technical sales associate. I wanted to thank you for taking the time to join us today. Before I begin with my overview of our nitrate sensor, I wanted to briefly introduce our group, Seabird Scientific. In January of last year, Satlantic partnered with Seabird Electronics and WET Labs to form Seabird Scientific. As individual companies and as a group, our focus is on delivering the most reliable data for scientists, backed by what we feel is the industry's best customer service. Currently, our development projects include integrated physical and biogeochemical instruments for long-term deployment platforms and creation of new measurement methodologies. Now, I'd like to give you a brief introduction to Satlantic and a general overview of our nitrate sensor, the SUNA. Located in Halifax, Nova Scotia, Satlantic was founded in 1991 by Dr. Marlon Lewis of Dalhousie University. We currently employ approximately 40 people, spanning from research and development through to production. As with both Seabird Electronics and WET Labs, we are very active in research and development, and we manufacture all of our instruments in-house here in Halifax. Our focus is primarily on optically based instrumentation, and we have several lines of sensors, as you can see at the bottom of the slide. Today, however, I'd like to specifically talk about our nitrate sensor, the SUNA. The SUNA was introduced in 2008 in response to a growing need for a coastal and freshwater nitrate sensor. It was developed from our existing ISIS sensor, which we first commercialized in 2003. This technology was originally developed at the Monterey Bay Aquarium Research Institute by Dr. Ken Johnson and Luke Coletti. The SUNA and ISIS have a large customer base in inland and coastal water quality monitoring, as well as in oceanographic applications. More recently, we have been able to integrate our nitrate sensors on many AUVs, including gliders and floats. Currently, our major customers in the U.S. include the USGS and the EPA, as well as university and government research, both domestically and worldwide. How the SUNA works is by examining the absorption of UV light by dissolved nitrate. A highly stable deuterium lamp emits ultraviolet light, which is transmitted through the sample over a 1 centimeter path length. The spectrometer detector then measures the amount of UV that has traveled through the sample. The algorithm we employ then calculates the concentration of nitrate based on the absorbance, specifically between 220 and 240 nanometers. On the left of this slide is a graph that plots absorbance of all known chemical species in the ocean environment. There is only one in this graph that can cause problems with nitrate absorption, and that is bromide. How we mitigate the effect of bromide on the nitrate concentration is by employing a bromide correction algorithm. This algorithm can be selected for use when the SUNA is deployed in salt water, or if the SUNA is deployed in fresh water, where bromide is very rare, it can be deselected. The other image is the amount of UV that is being detected by the spectrometer, and I've highlighted where we look at the absorption of nitrate. In this slide, I've shown an example of two spectra. The top spectra shows nitrate-free water, and the bottom shows a sample of water containing nitrate. The area in the red on the range of the spectrum is where nitrate absorbs. You can see that when nitrate is present, the curve changes, and this indicates an increase in absorption and therefore an increase in nitrate in that sample. Now on to some specifications for the instrument. The detection specifications for the SUNA are 7 micrograms per liter to 28 milligrams per liter, with an accuracy of 28 micrograms per liter, or half a micromolar to 2,000 micromolar with an accuracy of 2 micromolar. It is an optical instrument, so over time we do see some drift, which is very small. We have two versions available, a shallow version with a depth rating of 100 meters and a deeper version with a depth rating of 2,000 meters. The shallow version is what we recommend for coastal and freshwater environments, while the deep version we recommend for oceanographic and AUV applications. We have a wide range for power input to allow the user to connect the SUNA to any available power supply. And the sample rate for this instrument is approximately 1 hertz, or 1 sample per second. We also have employed a variety of telemetry interfaces, including SDI-12, RS-232 or serial, and analog outputs. The SUNA can be deployed in various scenarios, including mooring for long-term deployments or point sampling, as it is very small and portable. While most deployments are normally fully submerged, we also offer a flow cell that will allow for remote pumped applications or benchtop applications. One thing to note is that the SUNA does require external power and data logging for all deployments. When the SUNA leaves Satlantic, it leaves fully calibrated and ready to use. This instrument does not need to be recalibrated as it is in the factory by the user in the field. The only user calibration that is required is a simple re-zeroing of the instrument by refreshing the reference spectra. How we do this is using a software-mediated calibration wizard that walks us through the simple steps. It takes less than 1 minute, and it effectively re-zeroes the instrument and negates the effects of any drift that may have occurred. Aside from this simple user calibration, the only other maintenance required by the user is to keep the instrument clean, as it is an optical instrument, and we need to keep the optical pathway clear for the transmission of UV. We also offer many biofouling accessories for various deployments. We offer a copper foul guard, which is a perforated copper strip which fits over the optical pathway, and this prevents light fouling as well as debris from affecting the UV transmission. As I mentioned, we have a flow cell that can be used in existing pump systems, for example, integration with a WET Labs WQM, and for various benchtop applications. Our newest and most exciting biofouling accessory is the ZebraTech Hydro Wiper. This is a physical wiper which cleans the optical pathway and allows for long-term deployments and deployments in environments which have heavy biofouling. The software which we supply with the SUNA is called SUNACOM. It is available for both the PC and the Mac, and it allows for programming of the SUNA as well as real-time data collection. There are many other functions of this software, including the calibration wizard, which I previously mentioned, as well as reprocessing previously logged files. Now to switch gears, I'd like to show you some data that we've collected from the SUNA. In the first slide, I mentioned that we offer many different instruments, and one instrument that we offer is called the LOBO, or Land Ocean Biogeochemical Observatory. This is a collaborative effort between WET Labs, Seabird, and Satlantic. We have a demo LOBO here in Halifax. It's located in the Northwest Arm, hence it's called the Northwest Arm LOBO. This particular LOBO has several instruments, including the SUNA nitrate sensor. In this graph, I'm showing a series of data that was collected by this particular LOBO over a period of 6 months. And what I wanted to point out in this particular slide is the power that the SUNA has in acquiring a high-resolution time series of data. So in this graph, we have 4 different parameters that have been collected. The blue line is salinity, the green line is nitrate, purple is temperature, and red is chlorophyll A fluorescence. Now the northwest arm of Halifax is a very shallow body of water, and what we can notice with salinity is that occasionally there is a sharp dip in the salinity. This is indicative of a rainfall event in Halifax. And corresponding to each rainfall event and decrease in salinity, we also see a sharp increase in nitrate. And this is an increase in nitrate due to the washing of anthropogenic nitrate in from the fresh water. So as we can see, this is a very powerful tool to determine trends in nitrate and other parameters. This graph shows a separate test, comparison test between various optical nitrate instruments. This was completed by the USGS in New Jersey by Eric Vowinkle in the early spring of 2011. This particular data shows the results from a bucket test, in which these 4 instruments were placed in the same bucket with artificial seawater. We can see that the SUNA is able to accurately report the nitrate concentration in comparison to the other 4 instruments. In the same study, these 4 instruments were taken to various field sites in the Delaware River. And again, we can see that the SUNA most accurately reports the concentration of nitrate when compared to the other instruments. So we are very confident that the SUNA nitrate sensor will provide the most accurate data available in comparison to the other optical instruments available today. So in summary, the SUNA nitrate sensor is an optically based sensor capable of long-term, extremely accurate nitrate analysis. It has been developed for both marine and freshwater applications and is available for both environments without separate calibration. As it is an optical instrument, there are no consumables, there are no harsh chemicals required. And as I've shown, the sensor is very low maintenance to the end user. It is ideal for various deployment scenarios, including point sampling and long-term deployments and everything in between. The SUNA provides a high-resolution time series of data that is necessary for determining trends and monitoring water quality. I'd like to thank you very much for listening to my presentation on the Satlantic SUNA nitrate sensor. And now I would like to hear from WET Labs regarding their phosphate cycle P.
Good afternoon. This is Angela Hahn, and I will be introducing WET Labs. Giving an overview of cycle phosphate sensor is Corey Koch in our Science and Research Department. He will also go over the sensor design, software interface, and validation of the sensor with various case studies. WET Labs was founded in 1992 by Dr. Ron Zanefeld and Casey Moore in Philomath, Oregon. Our technological emphasis is on optical water quality sensors and systems for coastal and freshwater applications. We sell 7 families of sensors and systems that reliably provide accurate data about the inherent optical properties of the aquatic environment, including fluorometers, transmissometers, scattering sensors, turbidity sensors, and spectrophotometers, as well as, finally, the focus of our discussion today, the in situ nutrient sensor cycle P04.
So now I'm going to dive into more technical detail about the cycle P04. Cycle is an instrument that was designed to measure soluble reactive phosphate in situ. It has a detection limit of 2.3 micrograms phosphorus per liter. It's calibrated over a range of 0 to 0.31 milligrams phosphorus per liter, although it will perform above this range. It was really intended for long-term, nearly continuous monitoring. And so it could do over 1,000 samples before a simple field service, which we'll talk more about in a moment. And it can do up to 2 samples per hour. And try to make it as simple for the user to use as possible, it is factory calibrated to output phosphate concentration. So the user doesn't have to worry about calibrating the instrument or preparing the reagents. So in order to simplify use, we put reagents in simple click-in cartridges. These cartridges are keyed and color-coded so that you can quickly change them out in the field. They have a approximately 3-month shelf life, and the reagent chemistry and the analysis is designed such that these are temperature compensated from 0 to 35 degrees C. So these reagents are pumped into the cycle using micropumps along with sample. And this is mixed and then pumped into an absorption tube where the reaction happens, and we watch the molybdenum blue complex form, which is then proportional to phosphate concentration. So what's happening here is pretty much identical to what most people would do on the bench. For example, EPA method 365.5, or the classical chemistry first presented by Murphy and Riley. In addition, this titanium absorption tube is designed to minimize the effects of scattering or turbidity so that cycle is really insensitive under high turbid conditions. Sample comes in through these two anti-fouling screens on the bottom. These screens are made out of copper, and they're really just intended to keep macrofouling from growing over the intakes. And then the reagent chemistry itself actually keeps the inside of cycle from fouling. So after passing through the anti-fouling screen, sample goes through 10 micrometer filters. This is to exclude particles. Again, this was designed so that it can be quickly serviced in the field, so those filters can be pulled out and replaced, and the screens can as well. And that's really what comprises a field service, is changing the reagent cartridges and the filters every 1,000 samples. The cycle is designed to have a variable voltage input, so you can use different power supplies. It is a fluidic instrument, so it has pumps in there, and so there is a transient 2 amp peak current, but it was designed for long-term monitoring, so in general the current usage is low and it goes into a low power sleep state. It has RS-232 communications in addition to SDI-12 communication, and it has onboard storage, so you don't have to use it with a data logger. Cycle comes with complementary software, and this is a user-oriented GUI, and I'm just going to highlight some of the features of the GUI here. One is reagent usage tracking. Another is you can plot the raw data either in real time, or you can look at the phosphate data as it's acquired. It allows you to select the desired units that you want phosphate to be output in, and it has a deployment wizard that makes it simple to configure the instrument for different applications and set up a deployment schedule. To provide more confidence in the data that's collected in situ, one of the reagent cartridges, the blue one, is a Hach NIST traceable check standard. And so this can be programmed by the user to be used as a diagnostic tool to evaluate how cycle is performing. So what we're looking at here is over 6 months in an estuarine setting, the same cycle, just with the 1,000 sample field service. We compare our factory calibration with the phosphate determined based on doing a standard addition with that NIST traceable standard. And what we find is excellent agreement while in situ gives you good confidence in the long-term instrument performance. So another thing that gives us confidence in instrument performance is the ability of instruments to compare to one another. And this is really critical, especially when you're doing spatial studies, such as looking at phosphate uptake in a stretch of a river, for example. So here's a chart with 3 cycles tied together side by side in the field. And what you can see is that they track really well. And one of the reasons for that is every cycle has another NIST traceable check standard. This is mid-ranged, which is run on the instrument after calibration and after mock deployment to ensure that every instrument has an accurate calibration and they all will agree. We also evaluate this check standard when instruments come back for service, such that we can get an idea if calibration has drifted at all. And these are available to the user for them to test calibration. And then finally, validating the cycle P04 gives us the most confidence in its ability to perform long-term in situ. So over 2 years, we had several cycle P04 instruments, and they were lent to various partners. And these partners were tasked with grabbing samples. Here we're looking at over 125 samples. And they were supposed to, in general, use the same chemical method, but the way that samples were taken or the exact instruments they were run on or specific reagent chemistry beyond just the basic method wasn't prescribed. I think it paused. So what we're looking at here is over 3 years hourly of continuous phosphate measurements. And you can see the black X's. We had an extensive validation campaign in 2009 and 2010. And so what we have here is really a wealth of data, right? We can see long-term seasonal trends. In addition, we have high-resolution data, so there's a lot of depth to it. And we can actually zoom in on this data and start to tell more of this biogeochemical story, which really isn't complete without measuring phosphate. So what we're looking at here is a coastal upwelling period. And this upwelling period is characterized by water that comes up from deeper levels, and so it has higher salinity and lower temperature. And what happens with the nutrients when that water comes up is they've been highly mineralized, and so it's common to have phosphate and phosphorus and nitrogen at Redfield ratios of 16:1. And actually on this lower plot we have the axes of phosphate and nitrate at a ratio of 16:1. And nitrate is measured using the ICES, so that's a precursor to the SUNA from Satlantic, and phosphate's using the cycle PO4. And so what we see with these two separate instruments is that when the upwelled water mass comes into the bay, that the nutrients come into Redfield ratio, they begin to have the same dynamics. And then as those nutrients are drawn down, we begin to see significant chlorophyll fluorescence, indicating these nutrients have spurred a bloom. And it's really phosphorus and nitrogen together that help you understand the productivity in this system. And cycle is also used in freshwater systems. So here's an example of cycle in a small creek. So cycle is only partially submerged for this. And what we have here is a rain event that causes flash flooding because we're in an urban area that has a lot of impervious surfaces. And in tandem with cycle, there was an auto sampler, which was collecting samples, which were then later analyzed for total phosphorus. And so there's several things that we can see in this plot here. And so the first is the great relationship between total phosphorus and SRP. So we see similar dynamics. But as expected, right, the soluble phosphate is lower than the total available phosphorus in particles. And the other thing that we notice is that even with an auto sampler, you tend to gloss over some of the fine dynamics. And so there are these pulse events when you have these flash floods in small creeks that aren't caught by the auto sampler, but you see them in the gauge station in the discharge data. And then we also see phosphate variability that's associated with those flash pulse events, which without a high-resolution sampling or a high-resolution in situ instrument just wouldn't be able to be captured. And so to really wrap it up, cycle is highly accurate, provides high temporal resolution, so you can begin to have novel observations and capture events that you were not able to observe before. It enables long-term continuous monitoring, and that's in part due to a quick and simple field service and it being easy to configure.